Greetings everyone. The topic of our project is Reconnaissance using deep reinforcement learning. My name is Pranit Maldikar and my project partner Samir Dhole, and our project guide is Professor Shiv Negi. The aim of our project is to closely replicate biological systems for reward and translate this reward system and learning process for autonomous navigation of unmanned aerial vehicles or UAVs in unfamiliar environments using deep reinforcement learning. Talking about reinforcement learning, uh, it's there's an agent which takes an action A given a state S in an environment, and in return, the agent would receive a reward R and would transit into next state S dash. Also, another aspect of our project is detection of objects that are encountered in every frame using object detection models like YOLO V3. Our major goal is to develop and implement an algorithm for autonomous navigation that has a higher rate of convergence, that is, the time to reach the optimal learning as compared to existing algorithms. And here's an image from the real-time object detection YOLO V3 in action. As you can see, this is an image of traffic, and those are the anchor boxes.
Okay, so I'll take you over the presentation outline. The previous segment was introduction and aim. The upcoming will be the current scenario. After that, we'll tell you the solution to the problem. Then we'll go over our algorithm PPG 3D. Next will come the architecture and the autonomous navigation demo, followed by the object detection demo. At the end, we'll have the graphs, which are the testing results, and at the end, the references. Talking about the current scenario, we have UAVs that navigate based on collision avoidance only, and there is no learning based on the reward structure. Also, the application of the object detection for recon along with autonomous navigation is not implemented. The problem we are trying to solve is to implement a system that learns to navigate on its own in an alien environment based only on the state that it encounters and the reward that is generated by the reward structure. Also, avoiding local optima, that is suboptimal reward generation without navigation, should be avoided. Simulation softwares like Unreal Engine and Unity provide photorealistic environments for simulation. Currently, simulation interfacing softwares like Carla and AirSim provide state-of-the-art platform to conduct research on machine learning algorithms. Reinforcement learning algorithms for navigation exist in the form of PPO, that is proximal policy optimization, but they have a very long convergence time.
So we came up with a solution which is based on deep reinforcement learning. Reinforcement learning is a type of machine learning approach in which an agent learns to take the right action over time in an environment based on the state that it encounters and returns, that is, cumulation of rewards that is generated. We have stick to the actor critic architecture in reinforcement learning, where the actor takes an action and the critics optimizes that action, or we can say judges that action and returns up some values over which the actor can learn. The object detection part of the project was implemented using computer vision and tested with CNN modules. CNN stands for convolution neural networks models like YOLO V3 and YOLO V4. Here we can see the YOLO V3 architecture with an input image followed by a convolution layer, which is followed by a max pooling layer, and so on. So let's talk about phasic policy gradient, or PPG. We have used this algorithm for the implementation of the autonomous navigation part. This algorithm consists of two phases, the policy phase and the auxiliary phase. In the policy phase, agent takes the action with highest probability for that state following the current policy. After that, we optimize different losses and we collect the experience and store it in a buffer. In the auxiliary phase, we do not take any new actions, but we use this time to gain more knowledge over that experience and optimize the losses. So this algorithm was tested and implemented by OpenAI, and on this was done on 2D environments. So what we have done is we have implemented this algorithm for 3D environments, and so we made the following changes. We changed the loss functions. We implemented data structures for storing 3D data. Then we tried to reduce the time complexity over that data structure. And then we use separate actor critic neural networks. And we have used a neural network approach for function approximation, which is nothing but generalization of states to avoid infinite state
So this is the
spaces.
architecture diagram for our project. So our proposed algorithm, which is PPG3D, operates in two phases, that is the policy phase and auxiliary phase, as you can see in the DRL TensorFlow block. So initially, we have our 3D realistic environment in Unreal Engine. Then we use AirSim APIs to generate and retrieve various image data. So as you can see, we have the RGB image data that is retrieved, which is an input to the object detection part. We have a depth image and the depth image for the next time step, that is T+1, which is fed to the policy and value networks respectively. We also have the camera depth map DT, which is an input to the reward generation part of the project. Then the reward generation part is then an input, which is like that is the rewards that are generated are input to the policy phase. And again, in the policy phase and auxiliary phase, we have different losses that are optimized. So in the policy phase, the policy loss and the value loss is optimized, which are then back propagated to the policy and value network respectively. In the auxiliary phase, we optimize the joint loss, which is then back propagated to optimize the features of the actor network so that it can take better actions. At the end, the policy network or the actor chooses an action in the 3D realistic environment based on the maximum probability of an action that it thinks is the best. So these are the results for the autonomous navigation part of our project. So as you can see, the drone is navigating in the 3D environment. This particular environment is labeled as cloud. And as you can see at the top right corner of the screen, there's a map, and this environment has a lot of semicircular turns. At the bottom of the frame, there are three windows depicting three different cameras. The first camera is a depth image, the second camera is the infrared, and the third camera is the RGB image. The drone navigates based on the depth image as well as generates its reward based on the depth image itself. In the next environment, which is labeled as twist, you can see that it is pretty different as compared to the last environment. So this environment has a lot of sharp turns. So we see after training in this environment that the drone can learn in an environment that is semicircular as well as a lot of sharp turns. In the next environment, which is labeled as complex, this environment is the most similar to a real life apartment. As you can see, this environment has a combination of semicircular turns as well as a lot of sharp turns, but the drone has learned to navigate pretty well in this environment. The drone which is navigating here can be used in real life as a recon or a search and rescue drone, as this environment resembles a real life apartment pretty much.
So this is the object detection part of our project. And as you can see that the frame rate has slowed down a lot. This is because as the autonomous navigation and the object detection part runs simultaneously, they both happen to be computationally expensive. And we can average out these values, the accuracy of the object detection model, and we can say that the model is about 70% accurate. And this may be because of poor lighting or maybe overlapping of different objects. And this is the environment complex, which resembles, which closely resembles a real life apartment. And as you can see, the object detection model actually performs very well here. It can actually detect all the objects which can be found in any apartment, like a TV monitor, a dining table, a chair, and even the sink and the refrigerator. So these are the results for the autonomous navigation part of our project. We have used mean safe flight. Mean safe flight is nothing but the distance traveled by the drone in a given a certain time step, and which is represented on the y-axis, and the x-axis represents the number of time steps. And as you can see here, at any random time step, say 869, the value is much higher for the algorithm PPG than PPO. The numbers 119 and 194 besides PPG are nothing but the hyperparameters, that is the number of times the auxiliary or policy phase should be running. And for the next environment, we can again see here the red and orange line represents PPG, and the hyperparameters. And either way, you can see that the PPG has a higher convergence rate than PPO. And these are the results for the environment complex and long. The complex is the environment which has the closest resemblance to a real life apartment. And again, we can see that the algorithm phasic policy gradient PPG has a much higher convergence rate here. So in conclusion, I would like to say that we have successfully implemented an autonomous navigation system using phasic policy gradient and achieved the expected convergence. The proposed algorithm showed an 85% increase in the convergence rate when compared to the proximal policy optimization. The system can also detect basic objects like oven or a sink found in real environments with an average accuracy of 70%. And here is a table of autonomous navigation results. You can see that there's an average of 85% increase when compared to
So these are
PPO.
our references and acknowledgements. There are about 15 papers that we went through, and these papers are a combination of papers related to simulation softwares, reinforcement learning, autonomous navigation algorithms like PPO and PPG, different reward structures, and object detection.